So we're here to share this first case study. This is NYU Rubin Hall, a 15-story dormitory building in New York City. For those of you who are familiar with New York, this building is located just north of Washington Square Park. It's in a historic district called the Greenwich Village Historic District, so it's a landmarked building from the outside. The building is seeking EnerPHit certification, and we just started the construction phase of the project. So today's presentation is really focusing on the design phase and how our team had some challenging conversations, how we worked through it together, given the project constraints. This is something probably many of you are gonna have to do because we have a huge building stock in the country, in the world really, of existing buildings that need to undergo major renovations like this. And there's a lot of opportunity in that, and we should be taking advantage of it. So just our standard disclaimer slide. So our outline for today, oh, thank you. We're gonna start off with the project motivation. Why EnerPHit? How did we get to EnerPHit? We'll touch on the landmark status and how that kind of informed many of the discussions we had to have. We'll then show you the existing conditions that we were faced with and had to work with. We'll show you a unique opportunity we had to do a mock-up of some typical dorm rooms during the design phase, in like the early design phase, and that really helped inform some of the decisions we made. And then we'll get into some of the detailing, air sealing, windows, and walls. And really today's presentation focuses on the building envelope aspects of the project. We did also have a mechanical upgrade as well, but really all we could fit in today was the envelope side of things. So with that, I'll hand it off to Dylan.
Thank you. So why is NYU doing EnerPHit? So many of you probably work on many projects, and you know, I'm sure from firsthand, that you need a committed owner to have a successful project. It's no surprise to anyone. That's certainly the case in this project. NYU is very committed. They are such a large part of New York City that they actually are like more than 1% of the entire city's carbon emissions. So they know that they have to do their part. And what you're seeing here is their climate action plan, particularly their carbon emissions reduction goals. So their goal is to achieve a 50% reduction from a 2006 baseline by 2025, and ultimately net zero carbon by 2040. You can see where they were at over the years on the left, and the green bar is where they're currently at as of their latest data set, which is 2021. So there's work to do. And we engaged with NYU along with FX Collaborative and NYU itself to do a feasibility study of taking 3 of their buildings to the EnerPHit standard. And a quick shout out to Chris Ham, who's in the room, who actually was a big part of that, a major part of that study, of which I kind of picked up. So yeah, carbon emissions is a priority for NYU. They have to do it. They have to get there. And EnerPHit is viewed as the way forward for their buildings moving forward. But this is the first one.
So a little bit about the building. It was built in the 1920s as a hotel. NYU purchased the building in the 1960s and converted it to a dormitory, and it's been a dormitory ever since. Also in the 60s, they had done some renovations. So for those of you who are closer up to the monitors, you might be able to tell the windows look very different. So back in the 20s, the original windows were double hung. The replacement windows that went in were single pane, metal framed windows, casements. So they actually added in some dividing sort of muntins in between so that the casements were smaller. So being in a landmark district, if we're now going to try and hit EnerPHit certification, we want to replace these windows because they're not performing very well. And the Landmarks Preservation Commission, you know, we want to be good stewards of the building and of the neighborhood and make sure that the replacement windows, you know, are somewhat matching the original double hung windows. So we had to work really closely with window manufacturers. We did consider wood windows at one point, but NYU, you know, having to maintain 15-story building with wood windows, the repainting and maintenance requirements kind of push that out as an option. So we are using aluminum framed, high-performing aluminum framed windows with a simulated double hung effect. So the 2 panes of glass are actually offset. They're triple glazed, but they're offset with a larger dividing mullion in the middle that makes it look like a double hung, but it actually performs as a casement and a tilt and turn window. A couple other quick facts about the building. So it's 20% window to wall ratio. The slab edges account for about 14% of the facade area. So being that we couldn't do anything on the outside of this building, we had to add all the insulation from the interior. Those slab edges were going to be there. We had to deal with that as a thermal bridge and kind of live with it. Another challenge we had is each dorm room has 3 students in it. So there's quite a bit of furniture that gets crammed into these rooms. And if we're now going to add more insulation and encroach into that space, you know, FX Collaborative as the architect was like, hang on guys, we got to be really careful about how much insulation we put here because we still have to fit in that furniture into the space. So now I'll hand it off to Aris to talk about the existing conditions that we encountered.
Thank you, Cheryl. Yeah, so as you would with any building that is existing, we wanted to get our hands dirty. This is back in the summer of 2021. We wanted to make as many probes as possible, really understand all the intricacies of the existing building, understand what its exterior wall makeup is, what the surprises that we would encounter during building would be. So we started opening up the exterior walls right next to the windows, and we found that the backup behind that exterior landmarked withe of brick was an 8-inch terracotta block. And as you're seeing in these 2 photos, that terracotta block is hollow, and its thin, brittle walls have already started to spall. So Cheryl has been telling you we want to upgrade these existing windows to a deep aluminum frame, and the loads imposed from that new window wouldn't really go well with this existing wall. So straight from the start, we knew we would need some kind of frame to bring those loads imposed back to the structure that would be spanning slab to slab right behind our existing roof openings. Similar situation at the sill, we knew we really couldn't pick up the dead load there. Speaking of the existing windows, here's what those looked like. These are not the original ones. These are the ones that were installed in the 1960s, right around the time when NYU bought the building and converted it to a dormitory. So these are very narrow. You'll notice in the photo on the right, they are steel-framed windows, about 1.5 inches deep, and their relationship to all the materials that are adjacent to them in the roof opening is going to be significantly different than the relationship of the new, much deeper aluminum-framed, thermally broken windows. You also see on the smaller photo on the bottom that these windows are really reaching the end of their service life. All of the gaskets, all of the perimeter seals are starting to tear, and they're not airtight or watertight anymore. Taking a look at the windows from the outside, we noticed that some of the precast sills were cracked. The one you're seeing here is really the worst case scenario, and you're also seeing that this crack is propagating to the right through the brick masonry. We wanted to use this photo to bring up the fact that we are not the only design team currently working on the building. There's a whole separate other design team with a different builder that is working on a different scope. They're working from the outside to prepare a FISP report. This is a local law in New York. It's a facade inspection safety program. And long story short, the city is trying to make sure that the owners get a qualified exterior wall inspector to make sure that the buildings are safe. There's a lot of people walking under these buildings, bricks coming from facades, spalled terracotta, concrete, that can cause a really major concern. So we, as a design team working from the inside, doing this deep energy retrofit, have to work harmoniously with the other team working from the outside to be as efficient as possible for NYU, both project timeline-wise and financially. This is the last thing we wanted to show you on existing conditions. This is a skylight that's up at the main roof of the building. It's quite evident that this skylight is letting water in, and as you can imagine, it's also letting air in or out. So we wanted to figure out exactly where we should focus our detailing attention, and this is the design phase mock-up that we did back in summer 2021. Cheryl will tell us more about it.
Yeah, so we had a really unique opportunity. Just as we were kicking off design phase, summer 2021 hit, students move out of the building. And so NYU wanted to they took 2 rooms, they gave us these rooms and said, hey, we'd like to take a look at like some of the options for the finishes you're gonna put in. And we said, okay, well, can we use this as an opportunity to try out some of the air sealing detail we wanna try, maybe the insulation? And they said, absolutely, sure, go for it, but you have a very strict time window because students are moving back in August. So we had, basically about a month to 6 weeks to kind of get all this done. So you can kind of see in the photo the before shot of a room. You see the window is blanked off because obviously we couldn't get a window replaced in that short time frame. So we said, okay, that we're not going to include, but let's try and figure out the other detailing. The other thing we did was we did a blower door test of these typical rooms. So it wasn't necessarily a whole building blower door test, but we're trying to just understand the air leakage, not just to the exterior wall, but also between rooms, right? Show that the benefits of the air sealing between dormitory rooms. So the test before actually performed really well, and it might not be a surprise to some of you in the room, but the existing plaster and the multiple layers of paint over the years, it's actually a pretty good air barrier. And in the sort of after scenario, when the contractor had started to, you see the bottom photo, had started to sort of remove finishes and installing insulation and some of the detailing, that air test didn't perform as well as we had thought. And it was because of that, you're breaking that plane of the interior plaster, and they didn't do a good enough job sort of connecting the dots there. Again, all this was good information for us to then prove to the contractors later on, hey, these details matter. You gotta make sure you connect these dots. So that blower door test is just kind of showing, again, we sealed off the window because we knew we were going to replace the existing windows. We didn't want to include that as part of these tests. And then each of the dorm rooms has a bathroom in it with an exhaust fan. So we had to make sure we bagged and sealed that off as well as part of this test. And we used, tracer fog and sort of used that smoke to visualize and show NYU, hey, look at all this smoke that's going to the rooms, not just next door, but also upstairs and downstairs. So that was a really helpful exercise as a communication tool as well with NYU.
And we learned even more things. We learned that placing these electrical boxes on our exterior walls and trying to communicate to the contractor that we want them to be airtight is not going to be enough. So we actually decided to relocate the electrical boxes to interior walls where the risk for air leakage would be smaller. And admittedly, even if you have air leaking to adjacent dorm rooms or if you have it leaking to the doorways, it's not as bad as having this electrical outlet on an exterior wall. We also learned we would have to work around the shrinkage that closed cell spray foam would have around the perimeter of where we're installing it. So you see it here on the photo on the left, it's pulling away from the vertical stud, and on the photo on the right, it's pulling away from the head, the stud track. We also learned that we couldn't use any membrane we wanted to span the gaps and create airtight construction. EPDM membrane on the left really didn't like sticking to the paint and the plaster that was already there. The asphaltic membrane on the right with a nice coat of primer behind it did an excellent job of sticking to the plaster. And speaking of plaster, Cheryl has talked about it already. This is really, really old plaster. This is horsehair reinforced plaster, in fact. We wanted to use it as our air barrier. Since it was already there, it would be really expensive to demo it, remove it safely, do all of this kind of work. But we found out that once we started touching it, trying to remove a little bit of it, trying to detail it, trying to do things on top of it, it would really just completely crumble and fall off of the terracotta. So we decided to keep it in place, and we decided to install sheathing over top of it, which you'll see a little later. Dylan?
All right. I'm going to talk about the design phase aspects of the project. So one of the, I think, most interesting and challenging aspects of existing buildings, especially buildings like this, is the extent of both the thermal and the air barrier. So I want to focus in on the air barrier because that's what we're showing here in the outlined in red with the center of that highlighted in yellow. And essentially, what we're looking at on the left is probably the most challenging floor out of the entire height of the building, and that's the cellar level. So there are what's sort of at the perimeter spaces referred to as vault spaces, which are underneath the sidewalks of New York City. And if you ever walked on a sidewalk in a city, or particularly New York City, there's a lot of grates and a lot of openings and holes and things that we just can't control, or we don't know where air might be leaking into. So what we do is we define the air barrier at the perimeter of the vault spaces, and then the other really, really challenging aspect of this project is shown on the right side of this slide, which is the section of the building, and there's a penthouse level that a lot of the way that universities and institutions are set up is they have specific groups within the university or college that handle specific parts of the building. So one group manages the first 15 floors, and then another group manages the penthouse. And that other group has their own budget that they have to budget for EnerPHit. And there was not enough, I guess, time and coordination built in to be able to phase the retrofit of the penthouse level at the same time as the phase of the rest of the building. And as you can imagine, that makes things way more complicated because they're connected with the elevator. The elevator doesn't stop at the one group of NYUs and there's a new elevator for the other group. It's all connected. So there's, for one, going to be a phasing of the insulation in the penthouse level, which will happen maybe 2 or 3 years from now. But as far as the base building renovation, which is the lower 15 floors in the cellar, that's happening right now. The windows are the only real thing that's going to be replaced in the penthouse level. So we're relying on the air tightness of those windows alone and the air tightness improvements for the lower half of the building, or the lower 14/15ths of the building to achieve the pass-fail level, because by the time we do the blower door test, students are going to be ready to move in right after, and we cannot wait till that second phase. So that makes things really complicated, and it's a recommendation for projects moving forward to not try to do things phased, if you can. I understand it's sometimes just a necessity. You have to do it, but it makes things harder. These are just some photos of those grates. I don't have to go too much more in detail there. But as far as the detailing, on the left we have a plan view, and on the right we have a section. So Aris and Cheryl will talk a little bit more about sort of how we are utilizing a 1/4-inch dense glass as our sheathing layer because we realized, as our air barrier layer, because we realized that the plaster alone was not enough. That also requires tapes and joints to be sealed, and we also have a tricky detail at partitions that we're, we have a detail to help sort of address that corner, but testing will tell if it's actually airtight and if we need to sort of modify our thought for that. But the detail on the left shows exactly what we're thinking there. And then on the right, you can see a section, and there was a big decision point in terms of whether or not to go with closed cell spray foam or open cell spray foam, of which open cell was the decision from a moisture management standpoint. So, and again, Cheryl and Aris will talk about that. So, and thermal bridging is a challenge, and as Cheryl alluded to before, some of the thermal bridges you just can't deal with. But we do think that adding the high-performance triple pane thermally broken aluminum windows on this project will make the infrared image there on the right look a heck of a lot better. This was taken by Cheryl in the colds of winter, the coldest of winter, and obviously, as you can see, at the slab edges, at some vertical partitions as well, but really at the windows is the weak point thermally of the current condition. So we're going to improve that immensely. Okay.
Yeah, they always send the Canadian to go do the infrared images of the coldest night in the winter. So I know the text on this slide is too small to read. The point here with this is, FX Collaborative put together this great sort of isometric cutaway section of all this detailing that we were drawing. And this was an immensely useful tool to have as we were onboarding contractors especially. We could show them very clearly the design intent of, the continuous insulation, how it's supposed to be outboard of the, shafts for the pipes going up and down the building, showing how the plaster, or sorry, the 1/4-inch sheathing inboard of the plaster needs to be taped at all of the joints and corners and transitions. So, just another example of something that, I'd like to incorporate into more projects, because just communication is a big thing when you're trying to draw these 2D details, but you're trying to communicate how they connect in 3D space. it's a challenge, and there's a lot of miscommunications that can happen. Folks don't, bid the project properly, and then you end up in construction, and everyone claims scope creep, change orders, and that can be a real detriment to projects. Another unique thing we had on this project, as Aris mentioned, we started doing these probe openings to check out the backup wall construction. We discovered some areas of the building that had multi-withe brick in them that wasn't shown on the existing building drawings. So that brick was not in good shape, as you can see from the photo. It's pretty porous. So we collected a bunch of samples from different floors of the building, different elevations. We sent that to our lab to be tested. We tested it for things like compressive strength and freeze-thaw durability properties, but also for its hygrothermal properties, so that we could plug that data into WFI 1D software tool and simulate some of the insulation options we were considering at the time. So this is just an example of what one of the outputs kind of looks like. This is just the existing wall with 3 withes of brick and interior plaster. And then we simulated 4 different sort of scenarios of insulation on the interior side. So we compared closed cell spray foam, again, different thicknesses, because we were worried about fitting furniture in the room. And then we also tested open cell spray foam with a variable permeance vapor retarder at the interior side. And the one that won out in the end was the open cell case with the variable permeance vapor retarder. That case allows any moisture within the wall, right? Because it's still raining outside, that wall is getting saturated, that moisture gets absorbed into the brick and mortar. It's allowed to still dry to the interior. It's certainly slowed down a little bit by the added layers on the inside, but it still has that potential to dry out to the interior as well as to outside, whereas with the closed cell case, it's super vapor tight, even at a super thin layer of like 2 inches. Still vapor tight, doesn't allow that drying to the interior.
And let's wave our magic wands and get to 2023. Construction now. This is our real construction mock-up. This is what it looked like about 2 weeks ago. There's a window in there now. Thank you. So what you're seeing here is what we were talking about earlier, or that detailing that Dylan went through. The gray material is our sheathing, or gypsum core sheathing, that we have fastened through the existing plaster into the terracotta. We're hitting all of those fasteners with a tape or an air barrier transition membrane to keep them airtight. We're hitting all of the joints between the gypsum core sheathing with our air barrier transition membrane, and all of the perimeter joints. So wall to ceiling, wall to adjacent wall, wall to floor, everything gets a membrane on there. That's the asphaltic, the black membrane that you see. This is our window. This is the stock window that we customized in order to meet the existing landmarked windows. You see it's rather deep aluminum frame. It can accommodate the triple glazing that we needed. Its frame is insulated and thermally broken. And we're going to jump to our 50% CD sill detail now. It's quite busy. There's a lot going on. Let's just focus on one single thing. We like having 3-sided metal sill pans under our windows. Regardless of what kind of fenestration product we use, we want to have this fail-safe, basically, under our window, so that any water that gets under its sill gets captured by that stainless steel, in this case, sill pan flashing, and flashed to the outside. Dylan, why could we not do that here?
Well, as many of you know, who've done a thermal bridge model before, metal is bad usually, especially if it goes right through your insulation layer. So we needed to find a solution that was better than that, and thermally speaking, to help avoid the potential for condensation. And what you're seeing here is the thermal bridge models and psi values, or linear heat loss values. And if you can look at the numbers, which are in IP units, I'll cut right to the chase, they're really high. And the reason why is because we're insulating only from the interior, and the plane of the window is offset from that plane of insulation. So there was careful detail paid to how do we continue insulation as best as possible where the interior returns back to where the window plane is. But this was a major challenge, and we already had to deal with a lot of thermal bridging issues of which Aris mentioned. And this is just showing that in JAM, and you can really see sort of the bulging of the green section of the infrared image is really the area that we need to focus on. So one aspect of certification, for those that are interested, this project is pursuing the component path under the EnerPHit criteria. And the U value requirement of 0.19 is extremely difficult to achieve with good thermal bridge details. But when you have this situation of which the criteria does talk about where the insulation plane does not align with the window, and you thus have a very high window to wall installation heat loss value, the U value of the window goes up immensely. And that's what we're seeing here. So with a normal, if we were just to assume a normal window thermal bridge heat loss value, our 0.24 on average window U value would be more like 0.19. So that's how big the impact of that additional heat loss is. So I'm gonna hand it back to Aris briefly.
I think that's me.
Sorry,
Basically,
Cheryl.
okay, so the solution at the end of the day here, right, we had to get rid of the metal seal pan flashing, but we still are worried about the membrane that's below the window, because as installers are installing these windows, they're rough with it. It can damage the membrane as it's going in, and if it gets damaged, it's now concealed. It's really difficult to get to fix it. So the solution that we came up with was switching to a fluid applied, basically a more durable waterproofing sill pan flashing. So it's a fluid applied membrane, and it's reinforced with a fabric. It's a bit thicker, and it's just a little tougher. It can take a little bit of a beating. Certainly, if they're really rough with it, they can still put a hole in it, but it's just a little better than sort of the tapes and sheet membranes.
All right, and to wrap up here in the last 2 minutes, we're gonna talk about an exciting test that we did of the existing conditions. So we did a whole building blower door test of the existing conditions, which was really, really complicated, of which these shaft openings that you can see photographs of about half of them, particularly number 5, which is huge, and there's actually, you're seeing louver, an open louver to an open shaft into the building, and there's actually 3 of those louvers, so on 4 sides of that shaft. So these had to be sealed prior to doing the test, because we were worried that if we tried to pressurize the building with just a bunch of holes in it, we weren't actually going to be able to build pressure. You need some resistance to build pressure, and we were afraid we weren't going to build pressure. So what we did is we sealed those off and then tested the sort of sealed conditions. It took us about 10 to 12 blower door test fans to actually do this, and not all are even shown here in this image, so that's a heck of a lot. And we came up with about 60,000 cubic feet per minute at 50 pascals pressure differential, or 3.38 ACH 50. But again, with all open shafts sealed. Then what we did is we tried to estimate using some Air Barrier Association of America formulas of equivalent leakage area, but just running that in reverse, to estimate the additional air leakage from these open shafts that are just open year-round. And we estimate that that actually would bring the whole building sort of air leakage rate, if we were able to truly pressure test this in sort of the normal passive house conditions, of about 6 ACH 50. And for those that aren't familiar, though I feel many of you probably are familiar, the EnerPHit threshold is 1. So we're targeting about 6 times more airtight than what we estimate the building to currently be at. So we're making this building a whole lot better. We're not there yet. I wish we had a crystal ball or time machine to get there and let you know how it all went. So I'm sure there'll be some struggles along the way, but what's new? All right, and now thank you all for listening, and we're excited to hand it over to Ed and Dave, and we're also looking forward to a lively discussion.
So one more plug,
Oh, yes.
If you want to know more about this, we're actually going to be doing a webinar on this in November 2nd. So there's going to be an email that Ken will send out about it, but the whole team is going to be there. So we have obviously more folks that were participating in these conversations. So please, if you'd like to hear more about the project, sign up for that.
Thank you all.
Thank you.
So again, everybody, I'm Dave Parker. So on this particular project, I've worn some different hats in this industry for a little over 30 years. And on this one, I'm the passive house consultant, or I should say in this case, I'll call myself the sustainability consultant. We'll get into that a little bit more. But it was interesting to get to talk with this team ahead of this conversation, and how many common issues we ran into as we were developing the project, and actually similar solutions in many cases to what you're seeing here. But one of the themes that we kind of sort of honed in on was although in an ideal world, right, high performance buildings they may be easier to execute in sort of ideal conditions when you procure a project and you have the right owner and you have the right focus of the team and all that. But what kept coming up in the conversation was a lot of challenges that we found around the development of the project and communication on the project that just made building a really high-performing building really that much more challenging. So we'll talk a little bit about that. But anyway, thank you, sir. Appreciate that. So this building is our project in Pittsburgh. It's called Fire Station 8. It was built in 1929 as a police and fire station, like a combination station. As you can see, limestone facade. It's actually a very massive limestone facade. We have some very substantial masonry walls there. We're going to talk, again, a little bit quick overview. I'll start with that. We'll talk about some of the challenges we faced, and then I should have sort of introduced Ed as well. But so I was a sustainability consultant. I'm the sustainability consultant on this, and as I was going through a parallel process in time, this process started over 3 years ago on this project. I was also I was not only learning PHPP and doing my first handful of Passive House projects, but also starting to learn about the tools that Ed's developed, the Passive House tools, which he'll talk a little bit more about. And I really find them hugely powerful, and I think they've been instrumental for me and for our team on the project going through that modeling process, and he'll talk a little bit more about that. So that's the overview. So here's our location. For those of you who know Pittsburgh, the three rivers are evident there. Downtown Pittsburgh with the point is right in the middle. So we're in the East Liberty neighborhood, off to the east of the city, at elevation between 700 and 800 feet. There's the context. The building in the middle with the arrow on top is our station. A lot of new construction in this area, a lot of development going on. One other note on this slide, which I didn't realize until later, was in the upper left corner, where you see the dome. I don't know if I can point to it. That's actually a historic synagogue that is also being retrofitted for Passive House by another team. So it's exciting to see those projects right next to each other. So again, a little bit of the background. The client is the City of Pittsburgh, Department of Public Works. This is a 4-story building. As I said, it's a fire and police station. And then there's a sort of third component that has some aspects throughout the building that are available for the public and the community to hold events in and use for their events. So the history here is not a great one. This building has not been continuously occupied because there was substantial roof and masonry damage over the years, which led to ultimately initially, there was a complete move out, and then fire was able to come back in, but the police were relocated to a temporary headquarters elsewhere because of the significant damage. So when this whole project started in 2020, the RFP went out. It was considered a 2-phase project. There was actually a separate team with another consultant on board to develop a plan for the immediate masonry repairs, some modifications to the roof. There was a tall hose tower that was structurally failing, had to be removed, as well as to design a overall game plan to reach EnerPHit certification, which included not only the roof replacement, but a plan for an overcladding strategy around the entire building. So the city did not require certification, but the EnerPHit methodology and tools were written into the RFP. So basically, we're going down this path, but they didn't mandate certification. What they did do is set these reaching EUI goals, which you can see here, 32 kBTU per square foot per year, and 17 highly desirable. Now that was based, the mission critical goal was, I believe, 50% of the CBEX goal, or the CBEX number for public safety. So the building was also to be 100% electric, except they mandated a diesel-powered generator. That's the only fossil fuel source that we have on site. So there's the teams. I won't go through all this, but phase 1 team, Aris Group. Anybody here from Aris? So they had designed. Hey, hi Beth. Great. So that's how the project started, with this concept of this overcladding. And then phase 2 started as an interior-only completion of the project. But as I said, it got more complicated. So these are some of the challenges. So it started with actually this overcladding strategy, meeting a lot of resistance in the community, and ultimately going before the City of Pittsburgh Art Commission. And not only the design you see in this image, but a second revised design were both rejected. So the project wasn't proceeding down that road, so the owner stepped back and rethought the whole plan. We did a team conversation and kind of figured out a handoff to switch from exterior cladding and insulation to an interior approach, which is where we ended up. And some of the complexities to that involved the historic metal work on the outside of the building, which created some of the same thermal bridging issues that we were talking about earlier in terms of the metal elements penetrating into the thermal envelope, and also the windows. Because of the historic profiles, we weren't able to pull the windows back far enough to have them in line with the thermal. Also, those windows themselves very challenging because of the security requirements for the protection, which limits our thermal performance. So Ed will talk about the modeling process in a minute. I'll jump ahead just to quickly touch on another bit of complexity. So overall, the project, I should have prefaced this by saying, unlike this team, we're not yet going to construction. We've been told we're still likely to get out to bid, hopefully soon this year, but the project's been on hold for several months. It's been a lot of start and stop in terms of this process. And some of the start and stop involved just the coordination internally between the different organizations, right? The different Bureau of Fire, Bureau of Police, their own internal decision-making structure. So we've been reflecting on, I think, the workshop that Monty did earlier. I don't know if he's here, but we talked a lot about how do you design the workflow for Passive House to really optimize that schematic design investment. A lot of the decisions that we hope to be able to make during that process with the architect, we couldn't make because we couldn't get that decision-making process on the owner's side lined up in the right direction. So lots of challenges there. The last one I'll say is in Pennsylvania, if anybody's worked in Pennsylvania or intends to, we have a kind of unique requirement called the multiple prime contractor requirement, where from the Separations Act, which was passed in 1913, we can't bid to a single general contractor. So we have to bid for a minimum of 4 prime contractors. So the coordination effort of how do you set, and the project's also hard bid, so the coordination effort of how you set up all of this performance coordination and air barrier coordination and collaboration between trades is made increasingly challenging because of that. But hey, we'll have a go at it. So I'm not going to go through all this in detail. These are just a couple of snapshots of where we ended up. I mean, I'll say the general strategy. In our case, the plaster work is really substantial, and it was sort of the goal right now is to actually be able to use as much of it as possible, and then use a similar liquid applied flashing membrane around the openings. And we do have a liquid applied air barrier for other locations. Systems, it's not decoupled ventilation. It's as I say here, multi-zone VRF and DOAS ERVs. It's still optimized. We're still doing a lot of smart things to try to reduce energy in the building, and that's a snapshot of, there was a little bit of benchmarking available from the city, but it's not normalized, and it's not really, it wasn't cleaned up. So we just picked a number and said, if we say an average number of the years that we had available and to where we are modeling right now, we're looking to target about upper 70s to 80% energy reduction. So that's, we're still on track to make the buildings remarkably more high performing and comfortable, and we hope that we'll be able to move into construction soon and hopefully have another presentation in a year or so and tell you about the results. But at this point, yeah, I wanted to turn it over to Ed to talk a little bit about the modeling process and how we have been able to use his tools to facilitate building the PHPP in this case. So you got one right there. Yeah. Here's your.
Is this one okay, or should I talk? Does it matter?
I think use this one. Yeah.
Use this one. How's that? All right. Thank you, Dave. Hi, everyone. My name is Ed May. Nice to be here at the conference. Nice to see a bunch of familiar faces here. So I hope everybody's enjoying the conference so far. And I'm happy to be here to talk with you and share with you a little bit about the modeling tools and process that we used on this project, and talk a little bit about why we chose to undertake the methodology that we used, and then some of the differences between a building of this type what might you say, a normal passive house building, as normal as passive house buildings get. And so we'll talk a little bit about the tools. We'll talk about the sort of idiosyncrasies of this type of project and some things to consider if you are undertaking this type of work on your own projects. As Jonathan spoke about this morning in the keynote address, PHPP is a fantastic tool. It's a trusted, verified, well understood, well loved modeling tool used all around the world. We like PHPP very much. We use it for all of our passive house projects, obviously. But I do think it's important to recognize that PHPP has some issues and some challenges when it comes to large, complicated buildings with many different types of interior loads. That's kind of a mouthful. But basically, non-residential buildings with all sorts of different uses mixed up inside of them. Right? PHPP is really optimized for, let's say, single-family homes or even multifamily homes, works well on things like dormitories, any building where you have relative uniformity of internal loads. By contrast, with a building where you have some rooms or spaces that have incredibly high loads and other rooms or spaces that have very, very low loads, and we'll talk about the different loadings that you might experience. In those cases, the PHPP just becomes a very difficult tool to use, not so much in terms of the calculation of the actual energy balance, but in terms of the data management, the information management. We'll talk a little bit about how complex this building is and the different types of programs we have, but suffice to say that what we chose to do on this building was use a different type of building information modeling in order to try and capture and understand the nuance of the diverse loading down at the individual space level. Another important kind of thread to point out here, something that Dave brought up and Dylan pointed out when they were talking about the challenges with the different phasings there. You know, in our office, we have 65 active projects right now, and there's only 2 people in our office. We need to have the computer remember more of the information about these projects. We can't remember these projects. They start and stop. They get phased in weird ways. They disappear for a year and then pop back up a year later. The building information model needs to manage and understand and record all of this data in a much more rich and effective way. We just can't keep all this information in our heads. It's just untenable for the types of projects that we're working on there. So all of that said, what that means is I'm a big fan of using rich building information models to capture all of this data about our buildings. We have internally within our office been creating a set of these tools in order to allow us to do that. And this particular project was one of the important example cases that we used to develop that software. So we create software as we work through projects in order to solve problems that are very immediate. We need to get an energy model out the door by the end of the week, so we create software to help us do that as we go. And this project was instrumental in that process, and we ended up developing a whole host of tools around the particular challenges that we found in this project. So we use internally a set of tools known as Honeybee PH. I know that's a weird name, it's a long story. We use those tools in order to model all aspects of the building. So very similar to Design PHP, you model the envelope, of course. You also model all the plumbing, all the ducting, all the mechanical systems, and importantly, as we'll talk about, all of the space-by-space programs. And then all of that data is then pushed out automatically into the PHPP in this case. So that toolkit has been instrumental in allowing us to work on many and larger and more complex buildings. Why do we care so much about the internal loading? If you're more from the single-family world, you probably pay a lot more attention to the envelope. But one of the things that we find as we move from single-family and smaller residential to larger non-residential and more complicated buildings is that those envelope loads reduce as a proportion of the total energy consumption, and those internal loads, things like hot water, things like lighting, things like electric energy usage, those things begin to dominate the energy profile of the building. In particular, with passive house buildings, where we drive down the heating and cooling loads to a very, very low level, What you're left managing at that point, if you want further improvements in the building energy performance, is things like hot water and lighting and occupancy and sensors and pumps and fans, et cetera, et cetera. Now, for those of us who come, again, from the maybe single family world where we're focused on the envelope, that may be a bit of a bummer to start to have to spend all your time worrying about pumps and fans. But the reality of these buildings is that's really what drives the energy performance of them. And that's certainly what we saw in this particular building. Now, the other thing to note about this particular building, and this is not unique to this building, but this is very common for these types of buildings, is just the intense diversity of use type. These are just some example outputs from the energy model showing the room by room or space by space program, and each color corresponds to a different program. I'll talk about what a program is and maybe define that a little better, but let's just call it a usage, a type of space. You can see in the blow up there that we've got kitchenettes and elevators and washrooms and public lobbies all mixed together. That's just representative of one small slice of the building. So you have a huge diversity of load types, both when it comes to things like lighting, occupancy, ventilation, flow rates, as well as electrical energy consumption. And again, those things are really dominating the energy profile of this building, and it's critical to model those things and manage that data accurately and effectively within your building information model. I was reading a paper on the flight here. I know, that's weird, reading research papers on airplanes, but that's the kind of thing that I do. And in the paper, they were showing evidence, or they were showing some data that showed as much as a 90% performance gap between modeled or predicted and measured energy performance in these types of non-residential or mixed-use buildings. Properly baselining energy models and calibrating energy models to the actual usage profile and the actual usage mix within the building is absolutely critical if we want anything like an accurate energy model, so that we can then predict the best strategies or recommend the best strategies for reducing energy consumption. So again, managing that data down at the space level was absolutely critical. So what is a space within the building energy models that we're building here? Well, obviously it's going to have a whole host of geometric information around things like floor area and its sort of spatial configuration, its position, heights, and volumes. But then it also has all sorts of non-geometric elements, things like the hot water system or the heating and cooling system configuration. It's a complicated building with many overlapping and intersecting mechanical systems. It's important to understand on a space-by-space level which elements or which units are serving or delivering heating, cooling, or ventilation or hot water to the different spaces, again, if we want to accurately capture those nuances. What I've been calling a program so far is really made up of several smaller individual elements. Typically, we're going to talk about the program as made up of occupancy, lighting, and electrical energy consumption. Each of those, in turn, will have a load or a peak load and then a schedule of operation. So when it comes to the modeling, what we're doing is building out this whole network of loads and schedules, again, for each program type, for each space type. We might also add in the fresh air ventilation system. That's absolutely critical for a proper functioning passive house, of course, and then the modeling for that is really important as well. Sometimes the fresh air ventilation is going to overlap and align with our heating and cooling system, sometimes not. So we're going to have a different set of data for each of the spaces when it comes to the fresh air ventilation as well. Now that's a lot of data to manage. Again, and it's really important that as I said before, that the computer do most of the heavy lifting here. You cannot keep this information in your head. You cannot remember this information. It's vital that this data is encoded and managed within the building information platform that you're utilizing. Again, you're probably gonna put this project down for a year while the city goes out to bid, or you're in arguments with the top floor tenant, then you're gonna pick it up a year later, and you'll need to be able to go back to that building information model and tap right into that and begin working without a bunch of rework and going back and starting fresh. Here in this example, we're just showing one small view here showing how we can, for instance, query one of the program types. We end up building out a whole let's say, a catalog of different program types where we can then query them. In this case, we happen to be looking at the large office type, the closed office subtype, and then within that, you can see here that we have a people per area, right? So this is kind of the network of connections and hierarchy of data that we end up building for all of the different space types, different program types. This is just one example of how we might manage some of that data on the loading side. So for each of those program elements, we have a load, and then in parallel, we have a schedule of operation. Now with a building of this type, with these style of buildings that have very diverse loads, many of them are also gonna have very diverse schedules as well. Again, unlike maybe a typical residential project where the usage might be relatively straightforward, in many of these types of buildings, you might have spaces that get like this room here, that gets significantly loaded for a few hours a month or a few hours a year, and then the rest of the year they lay fallow and they're empty. So that's the kind of nuance that we want to begin to capture in these models, again, if we want something like an accurate prediction of energy consumption. Here you can see just another small vignette of the hourly energy model, and in this case, we're going to be adapting that and converting all of that rich hourly data into the annual average schedules that are used within the PHPP. As I said, there's a lot of data to manage. You don't want to be building out this data for each of your projects uniquely. You want to tap into the existing data sets that are available to those of us working in the United States. The tooling here, for instance, allows us to automatically deploy any of 23 different building typologies, and then within those, we have a huge range of different space types. On the listing here, you can see everything from IT rooms to lobbies to washrooms and storage rooms. All told, the tooling here has, by default, something like 1,700 space level programs. Again, each of those space level programs has a lighting, a fresh air ventilation load, an occupancy load, an electrical energy load. So we're talking about, again, about a tremendous amount of data. You want the computer to manage this. You do not want to be doing this yourself in spreadsheets or by pencil and paper. For this particular project, we had a great mechanical engineering team that we were working with that was using an hourly tool, the HAP tool from Carrier, in order to do the mechanical engineering design. And it was important for us to try and align those different models. And so one of the steps that we took here was to try and get as much data as possible from the mechanical engineering team's peak load model, and then adapt that for use in the annual energy performance model that Dave and I were creating there. So what we got issued from the mechanical engineering team was just basically a text document. We had to create, again, custom software in order to extract the data that we needed from that, and then automate the way that that flowed into the PHPP style schedules. All of that conversion gets done automatically using, again, some of the custom software that we create internally. So we take what are typical United States Department of Energy style, Energy Plus style hourly loads and schedules, and we adapt them to the peculiar dialect of the PHPP. Instead of inputting occupancy, we input absence. These kind of, it's not hard, it's all just math, but you need to adapt and sort of translate the way that we speak loads and schedules in typical energy modeling world here in the United States into the dialect and the language that's spoken by the PHPP. So the tooling here does all of that heavy lifting as well.
Okay, thank you,
Sorry.
Ed. No, I think as we were talking about recommendations, I mean, I think one, if you're going to take on I guess I'll speak first to sort of the consulting community, architects, designers, and whatnot, and say, if you're going to take on one of these projects, be prepared for what I would call, in my experience, a relatively unique level of complexity to get to a very high-performing outcome. I've worked on a lot of retrofit projects, but it wasn't until I got to this level of performance goals and the challenges that we had on this particular project before I really saw, kind of what the level of challenges and the scale that you could face. Do not underestimate the data and information management side of this effort. This is, I'm a handful of projects into my Passive House career, and this was an enormous amount of complexity and data and information to track. And I'm not, that's not really my field. So I would say be prepared for those levels of complexity. Look for tools And if not, and I think Ed can speak to this too, look for tools that will assist you in that process, or create your own and share them. And let's learn from these kinds of efforts, because I think as more of these projects get taken on and we have the opportunity to sort of build more powerful and more agile tools, it'll speed the ability of teams to be able to get on board to do something like this and deliver better outcomes to owners. So I would say generally those are my recommendations, but at the end of the day, I would say from my experience in this project, I mean, when it comes down to the nuts and bolts of the construction intervention, the sort of physical delivery on this side of thing, these projects are absolutely doable. We may not be able to get to 100% certification, but using the EnerPHit strategy and methodology and the tool sets, this is the way to get to the highest performing outcomes you can get. So we should be talking to every owner about this opportunity. So I guess that would be my recommendations. I don't know if you want to
That's great.
add anything to that?
No, I probably shouldn't speak.
All right, thanks very much.
Thank you so much for everyone on the panel so far. And I'm going to kick you off with a question, but then I'm going to take a seat with you guys and let you ask each other some questions. But when it came to working with the clients, and if the client was the owner or if it was a committee, and then the builders as well, when they set their EnerPHit goals and they started to try to achieve those goals and learned from all of you as a team about the studies you were doing to show them the benefits, how much did EUI, energy usage intensity, or return on investment play into that? And how did you educate the client so that they could achieve their own goals instead of getting in their own way? So I'll start with you guys, because you started us off. Thank you.
So in the NYU context, I'm probably literally going to steal words out of Cecil Schaub's mouth, who is the sustainability director at NYU and is one of, if not the most important reason as to why NYU has made their commitments. EUI is obviously important, and largely due to that graph I showed at the top of our presentation in terms of their carbon reduction goals. There's obviously a clear correlation between carbon emissions reductions and EUI reductions. One thing I don't know if we mentioned, but it's an all-electric building as well, with heat pumps for hot water and for space heating and cooling. So it's really going for it in terms of the lowest possible EUI in these buildings. But I think an even maybe bigger driver, or equally as big of a driver, is improving student life. And one of the things that he says is, when he gets the question of, is going to Passive House more expensive, is that worth the investment? And they've done life cycle studies that show, over the lifespan of this building's life, it's, on order of less than $10 per student. That is addition to getting these co-benefits of Passive House design. And those co-benefits being improved indoor air quality, improved thermal comfort, improved acoustical comfort. This translates into likely more productivity and better well-being amongst students living in this dorm building, and having to study and do what they have to do. And if I were to ask our student life folks if you would invest that in your students, the additional $5 to $10 it takes over the life of a project, keep in mind how much tuition is and how much goes into how much money sort of goes into these projects. The answer is always absolutely, we would spend that. Like, why would we not? It totally makes sense. So I think they're trying to bridge the gap between these benefits that are not as easy to quantify in terms of a cost savings, but these sort of co-benefits to students. So it's EUI, but also equally as important, those co-benefits.
So echoing the keynote, different priorities.
Yes, exactly.
That have a tremendous amount of value.
Yes.
Thank you.
Well, I guess as I said, for our project, I came into the project sort of in a phase 2, and I would say that the Aris group has been working, as I understand it, and Beth can correct me if I'm wrong, but for many years with the city and multiple stakeholders within city administration to try to help encourage these kinds of projects to be developed. So I wasn't actually in the room with those conversations about how the team kind of came up with these goals specifically versus other goals. But I would say, it was clear from the city's project manager as we started the project that there was an intensity of commitment behind going as far as we possibly could, even acknowledging some of the challenges that we knew we were going to be facing. So I can't really speak to sort of the history there, but I mean, I believe this has been a multi-year process of ongoing communication and education and efforts to have these conversations, which I think what Dylan said, I would just sort of second that it seems always uniquely important to not just let these conversations kind of break down to its dollars and cents and its kilowatt hours and those kind of, like, there's a point at which that has a diminishing return in terms of engagement, I think, but what can you get people excited about are these co-benefits and these sort of additional value adds that you have with Passive House. So yeah, that's kind of where we came into the whole owner conversation. Hope I answered your
Considering
question.
the benefits that we have on climate change and the impact of the cost of that, it's a benefit that is beyond quantifiable. So do you guys have any questions for each other about your projects before we open it up to the audience? Or shall we open it up? All right, any questions?
Open it up.
Michael?
Hey, folks. First of all, two great projects. So for those of the folks here in the audience who might have one of these cool projects come across their desk, what are the first 1, 2, or 3 things that you would do, having done these? What would they do first to make sure that the next steps after that follow through? Like, call your Passive House consultant first. What are the first 2 or 3 things that you would do to kind of make sure the process kind of goes smoothly, especially if it's someone's first time?
Well, I can start and maybe hand it over to either Cheryl or Aris here, because I think a feasibility study to get to Passive House, assuming that the client is aware of the benefits of Passive House and understanding, what that means for them. A feasibility study is always a great first step to understand at a high level, what sort of R value do we need in our walls? How good of a window do we need? What's our heat recovery efficiency need to be on the ventilation system? Also understanding how much ventilation needs to go in and out of the building. Those high level questions, understanding that I think is a key first step. But then I'm gonna hand it over to SJ to talk about the existing conditions.
Yeah, so we're talking about in the context of retrofits here. So getting to the building, walking it inside and out, getting into every space you possibly can get into, making those probe openings, get as many probes as you can because you never know what you're gonna find. Remove a window, right? So you can see what the rough opening conditions kind of look like. What are you detailing to? What are your membranes going to be sticking to? Because if you can plan ahead for those things, right, the earlier in design you can account for those things and cost them, budget for them, the better off you'll be. Those surprises that you find as you move through a project and you get to like construction phase, all of a sudden the cost may be 2, 3, 4 times higher than if you had caught it earlier on. So that sort of feasibility combined with like a condition assessment as early as you can in these projects is what will lead to success.
I guess I would sort of pick up on that, this idea of the physical reality that you're facing. There's the sort of technical modeling aspect of these projects, but to me, just from my own personal experience and spending some time in construction, I've learned as an architect, I will say that the years I spent in the field, I probably learned more about construction in those years than I ever did in CA, visiting the site every couple of weeks and that sort of thing. So I would a couple of things. One is I think Dylan answered the question in terms of who goes first. Like I'd love to see the Passive House consultant in the room as early as possible. And I'd back that up by saying I'd love to see the contractor at the table too. These publicly funded projects in Pennsylvania, I don't have the data to back it up, but anecdotally in conversations and project, talking to teams that have done these projects, there's a lot of conversation about how this kind of delivery method and the procurement limitations that we have limit the ability to collaborate with all the stakeholders at the table. I personally firmly believe that I would advise every owner to align with a builder or find some way, if you have limitations in your funding schemes for whatever reason, to try to get some specialty trade and some general trades advice, even third-party disinterested, just to have, when we're having these conversations as designers, I've just found those kinds of collaborative conversations to be the most valuable. And I do think ultimately in a very unstable supply chain environment and high cost construction environment, which we're probably likely to be in for the foreseeable future, having, again, the delivery side at the table and even supply chain at some point to collaborate on coming up with these solutions is super important.
Specification and early design. Yeah.
Yeah.
Thank you. Another question?
Great job. I did have one question, I guess maybe for both projects on a technical end, because I think structural thermal bridging is certainly a major issue with these types of interior retrofits. And I don't believe we saw the details around what you guys did at the floor slabs and the impact of kind of those slabs on the design and whether or not there was any specific approach, to mitigate that and mitigate not just the thermal bridging from an energy performance perspective, but also condensation control perspective. And I don't know if you guys can speak to that particular detail.
Yeah, I mean, I believe we have a detail that we did a slight return with a small piece of insulation. I should have mentioned, Todd, too, it was mineral fiber and, basis of design for the interiors wall assembly. But we modeled both, and we actually modeled a couple different variations of that. And looking at the relative impact to the whole model, it was not as significant actually as I anticipated initially. So it's a bit of a learning process, but we have a small return at the ceiling level, and that's where we are at this point.
And Cheryl, didn't you mention that the slab edge was like 10%
Like
of?
14% of our facade. Yeah, it's a huge amount of the facade, and it's something we just have to model and account for essentially in the process. So you put that in, and then you figure out, okay, how much insulation do I need to offset that? So that's how we did it with our project.
And you had two good details for the strategies on how to mitigate that edge and also the steel.
Yeah, we
Ground
also had
points.
the partition walls between dormitory rooms, right? They weren't going to demolish those to run the insulation continuous. And also they had to be a fire rated partition as well, so you couldn't break that plane. So yeah, we ended up with just butting up against it, and same with the air sealing detailing, yeah.
Well, how much was the envelope the driver of all of the efficiencies for both of these projects for you?
I mean, for us, it was huge. And I will say the air sealing detailing was huge because, as Dylan pointed out, right, we're like 6 times more tight. And our mechanical engineer, AKF, really showed how, hey, the mechanical systems, the sizes of them is substantially lower if you can predict and sort of account for a good airtight building or good airtight envelope after the fact, right? If it's just an unknown and they have to kind of put a safety factor on the air leakage rate, they're going to oversize their systems, and that adds cost, that adds material. So yeah, the envelope really drives the mechanicals.
And airtightness over insulation and vapor open over closed,
Absolutely.
given the
Yeah.
brick and the existing conditions.
Correct.
I would say it's a great question. I would say for the project that we were showing here, it was a little bit the opposite. I would say that the internal loading, the lighting, and then the ventilation system flow rates were really the driving factors in total. It's not that the envelope wasn't important, but in terms of like the key drivers of the energy performance in the places that you could really move the needle with some relatively small tweaks and changes, it was really more on the system side, and then on managing things like lighting, through straightforward techniques like dimmers and daylight sensors, stuff that we all know, but when you see it in the model, you go, oh, geez, that's really, if you really ran those lights 24 hours a day at this lighting power density that you're proposing, like, that would be a problem.
We need a whole passive house accelerator on just the data that you were pulling out, because then 0 occupancy to full occupancy, like over,
Right.
that was fantastic. I can't get enough of that. So.
I understand that you guys didn't have the option to build new, but is it cheaper, is it better to build new or to retrofit based on your experience?
Oh, that's a big question. Big ending question.
Yeah, I'll answer that. It depends.
Perfect. You got the Harvard answer.
As straightforward as you can give me, I would really like to know.
Well, the reason I got, what motivates me to push myself in this space and try to see how far and how fast we can move in passive house is to make the biggest impact in the shortest period of time. And to me, that's retrofits. And so fundamentally, the challenges of cost and complexity and all those other things have to be weighed against how can we make the biggest difference in the shortest period of time. To me, there's not really I don't vacillate about that. I'm not terribly interested in new construction anymore. Really just want to see if we can get really creative on retrofits and scale as fast as we can.
And if you're looking through the lens, it depends what lens you're looking through, right? And what you're valuing and what your priorities are.
What
If you're
about
looking-
money? That's
well,
the lens I'm looking
then
through.
you're
is
using a
cost.
paradigm of value that got us into this mess in the first place. But if you look at it through the lens of climate change and you think about embodied carbon and all of the building materials and the manufacturing and the transport that go into those, that's 50% of our 2035 and 2050 goals. So that 50% is very, very valuable when it means changing the paradigm of how we build and pushing this envelope of building better buildings and reimagining this. Okay.
Yeah, and just to add on to that, I mean, there's a schedule impact which impacts costs as well. So for example, on our project, the amount of time it would have taken to demo all of that plaster and the schedule risk it introduced was also played into that cost conversation, but it's also an embodied carbon conversation too, because if you're demoing all that plaster and throwing it into a landfill somewhere and then bringing in a new material, right? So it kind of goes together. I think retrofit is the right way, for these buildings. And when you think about schedule in addition to cost, it does sort of work out. Yeah.
And there are some buildings that we knock down because of the feasibility of trying to retrofit them versus renovate them. But they're all their own special flowers. And if you love old buildings like we do, so many of them need to be saved. And this is the way to do it. So we're going to wrap up. I want to thank all of our speakers today. Thank you all. Thank you all for attending.